Hello, my name is Nastasia Masalova. This is my lab report on the topic of motion of a falling object. The main goal of the second lab is to record and analyze an object that moves at a non-constant velocity in a vertical direction under the gravitational and air resistance forces. This experiment is important for me because it shows how a non-zero net force influences a moving object. Additionally, understanding motion with a non-constant velocity is essential for learning more complicated motions later in the course. Before I elaborate on the experiment and the results, I want to cover several concepts and formulas that we will need for analyzing the motion. Newton's second law or momentum principle is the main concept for this lab. In the experiment, we consider that net force is a non-zero value because of the acting gravitational and air resistance forces. According to the momentum principle, the velocity will not be constant. For this lab, we will consider two computational models. One of them will predict the object motion under only the gravitational force, and another one will predict the motion under both gravitational and air resistance forces. On the slide, you can see the formulas we will use to compute the net forces. As a preparation for the experiment, I found the mass of a paper sheet that I used to make a ball. After that, I recorded the video of the falling ball and analyzed it in the track application. After tracking the ball's position, I created a table with observed values of time and position. One of the important values I got after tracking the ball's motion was its initial position vector. Since the object started moving from rest, I considered the initial velocity to be 0. To create a computational model, I also needed starting time, market frame, and final time values, which I got from the track application. For the first model, I considered that net force is equal to the gravitational force only, which I computed by using a formula: force of gravity equals to minus mass multiplied by gravitational constant and unit vector. With this data, I wrote simple code in GlowScript to generate computational model of the moving object. After running the program, I observed a 3D motion of my model and analyzed two graphs: position versus time and velocity versus time. I also created a table with predicted values of time and position. After the first model, I created another computational model with the same initial values of position, velocity, and time. However, this time I considered air resistance in my computations of the net force. I found the air resistance force by using the formula force of resistance equals to resistance coefficient B multiplied by the velocity of the ball squared and unit vector. I found the terminal velocity by analyzing the time velocity graph of my observed ball. Then I wrote a momentum principle for the moment in time when force of gravity equals to the force of resistance and solved an equation for B. After running the program, I observed a 3D motion of my model and analyzed two graphs: position versus time and velocity versus time. I also created a table with predicted values of time and position. Finally, I created a chart with 3 lines that represent 3 functions: observed position function of time, predicted position function of time for a motion without air resistance, and predicted position of time for a motion with air resistance. Graphs of observed motion, blue curve, and predicted motion of an object that is influenced only by the gravitational force, red curve, are not identical. The difference occurs because we assume that air resistant force does not exist. However, in the real-life setting, the air resistant acts on the falling paper ball. Graphs of observed motion, blue curve, and predicted motion of an object that is influenced only by the gravitational force and air resistance force, green curve, are almost identical. The difference occurs because we cannot precisely define terminal velocity, since the object doesn't reach the velocity over a small interval of time. As a result, the predicted air resistance in a computational model differs from that in an observed motion. After conducting the experiment, I needed to give answers to 2 questions. The first of them asks which of the models I created predicts a terminal velocity. By looking at the chart, we see that the computational model that considers air resistance predicts the terminal velocity, which is approximately minus 3.5 meters per second. The second question asks to predict terminal velocity in a scenario where the ball is thrown downward initially, which means that the initial speed was a non-zero number. By looking at the equation of momentum principle, when gravity force equals to the air resistance force, we see that the terminal velocity does not depend on its initial velocity. Therefore, the terminal velocity will be the same, approximately minus 3.5 meters per second. Thank you so much for watching my video. Hope to see you in my future labs.